API 574 Piping Inspection Practice. Chapter 4 Piping Components. Piping of a nominal size larger than 16 inch is usually made by rolling plates to size and welding the seams. So this can be a potential exam question. Which sizes of the pipes upwards are made by plates, by rolling the plates and welding, or welded pipes are. So it's 16 inch and above. Pipe wall thickness are designated as pipe schedules in MPS. So in all standards, the outside diameter remains nearly constant regardless of the thickness. So when we say MPS 4, the outside diameter is same. It's not exactly 4 inch, but it's same. Slightly more than 4 inch. The size refers to the approximate inside diameter of standard weight pipe for MPSs equal to or less than 12 inch. So as we said, the schedule is directly related to wall thickness. As the schedule goes up, the pipe thickness goes up for the same MPS number, and also it is directly related obviously to the inside diameter, because as the thickness goes up, the inside diameter reduces because the outside diameter remains the same. So the reduction should be from inside then when the thickness goes up. MPS, nominal pipe size. Remember this, sometimes exam question are as easy as this. What MPS means? Nominal means the diameter of pipe but not the actual size. The European and international standard IS designation equivalent to MPS is DN, diameter nominal or nominal diameter. For example, MPS 1/8 corresponds to DN 6 with an outside diameter of 0.405 inch or 10.3 millimeter. The thickness of pipe is determined by schedule, as we said, and as you can see from this table, at the inside diameter, the less the ID, the thicker the pipe and heavier it is. So all pipes with a unique MPS have the same outside diameter, but depending on their schedule, their inside diameter and weight changes. As you can see here, 1/8 inch MPS 1/8 DN. Normally they say this is dimensionless. It's a DN 6, so it doesn't mean anything. It's just a number designated to this MPS 1/8. So the OD is 0.405, and for schedule 5S is 0.035 inch. And as the schedule goes up, the thickness increases. The outside diameter remains the same. Table 1 and 2 show the relationship between MPS, outside diameter, as well as the schedule versus inside diameter for various pipe sizes. And table 3 shows permissible tolerance in diameter versus MPS and thickness or schedule for ferritic pipe. The actual thickness of seamless piping tolerance is permitted up to 12.5%. You can see this white tolerance is because the manufacturing techniques drawing normally is used. It's seamless, it's just one piece. So there is a white tolerance here, it's 12.5%. This might be an exam question. However, the welded piping can only be 0.01 inch thinner than the manufacturer's stated thickness. This is because the welded piping made of plates, and according to ASME section 8 and other codes, the plate cannot be thinner by 0.25 millimeter or 0.01 inch. And hence, once it's the same rule applies when it turns in rolled and turns into a pipe by welding. Casting is brittle and not used for pipe process industry. So you should remember it. Casted pipe are usually used for utilities drainage, water pipe, etc. Non-metallic pipes such as FRP or GRP, fiber reinforced plastic or glass reinforced plastics, used for utility services such as water and sewage, because they are not isotropic. They don't behave the same way in all directions stress-wise, and they are not that. There is no much confidence in the industry to use them as a high-pressure pipes. FRP and GRP made of resin epoxy called binder, and reinforcement made of fiberglass. FRP does not corrode but can deteriorate over time by ultraviolet sun ray. But many FRP pipes fail because of poor manufacturing practice. So the main cause of failure of FRP is poor manufacturing practice. Quality is very important for the pipe reliability for FRPs. FRP patches is also frequently used for temporary repair of pipes. I've seen it on many offshore, especially offshore locations where you could not shut it down and you could not replace the pipes. So you apply a few patches of FRP as a temporary repair until the next shutdown or turnaround, where the pipe would be replaced. The advantage with FRP pipe is quick manufacturing with minimal wastage and can be easily custom built, because it's like a cast sort of. It forms the how you do that. There is no machining involved here. There is no discarding any extra materials. So FRP, unlike metal, is non-homogeneous, and hence NDE examination is limited and difficult to detect the damages and defects. Therefore, emphasis should be placed to stringent quality control during manufacturing. And because of its nature, there is resin and fiberglass, and because it's non-homogeneous and non-isotropic also from stress point of view, there are several techniques developed, but so far there was it's not quite easy to scan or UT and FRP fiber reinforced plastic. Tubing is generally seamlessly drawn. Valves. Piping inspector shall have basic knowledge of valves, API 574 as explained, gate, globe, plug, valves, API valves, ball valves, diaphragm valves, butterfly, check, and slide valves. The applicable standard for these valves are API 599 and 600, up to 609. Now, gate valve is generally used to either completely shut off fluid flow or be in fully open position. Gate valve consists of valve body, seat, and disc, a spindle, gland, wheel for operating the valves. As you can see, this is a gate valve. You just allow in or out. Valve are primarily designed to stop, start, and regulate the flow by turning the wheel, thereby moving the disc up and down. Flow regulation is accuracy improved by steep tapering of the seat. So flow regulation accuracy is improved by steep tapering of the seat. As you can see here, it's not 90 degree, it's at an angle here, so that the globe can sit on the seat, so and then make it lift tight. This is the seat, as you can see. Plug valve has cylindrically or conically tapered plugs which can rotate inside the valve body to control flow through the valve. Valve is open when the opening in the plug is in line with the flow. By turning the plug by 90 degree, a quarter, the flow would be completely closed. You can see here there is a hole inside. So by turning it 90 degree, it opens fully, and then turning it back to its original position, another 90 degree, stops the flow. Ball valves control the flow by a rotary ball having an opening. Again, as you see here, it's got an opening. And then again, by turning it 90 degree, the valve can be open or closed. Very good for leak tie services and is extensively used in the industry. So most of the valves, they got their name from the actual controlling mechanism for regulation of the flow, like gate globe. Diaphragm valve moves up and down the opening and closing the flow. Diaphragm valve is good for corrosive service because the diaphragm and sealing are non-metallic. Not suitable for high pressure because they are non-metallic, so they are not suitable for high pressure or temperature applications, high temperature, and hence not widely used in the industry. As you can see, push the diaphragm and then it closes the flow, and then you push it up and then it opens. Butterfly valve. When the valve is closed, the disc is turned so that it completely blocks off the passageway. When the valve is fully open, the disc is rotated a quarter turn so that it allows an almost unrestricted package of the fluid. Butterfly valve is used for low pressure application with not so accurate flow control. Now, normally it's either fully open or fully closed. You can put it half open, but then there might be a lot of wear of displays. As you can see, this is like a wings of a butterfly. So, and hence the name. Check valve allows flow in one direction and automatically prevents backflow, reverse flow when fluid is in the line reverses direction. So as you can see, it can be go this way, just one plate. It can be two plates with a hinge in the middle. There are different methods. All this, so it goes up. If the flow comes back, then it closes. So it is always open when it is at the direction of the flow, and it closes when the flow reverses back. As you can see here, there is a lock here. So it can just move in one direction. It can go up and then come back to its own position. As you see here, now this is a closed position. And if the flow comes, it will move up and allow the flow to pass by. Slide valve, it's like a guillotine. Another version of gate valve, but with a sliding action like guillotine. The internal part, and especially the slide, is susceptible to wear and hence protected with erosion resistant alloys, not gas tight. So this is another valve. We have several fittings used to either connect the pipe or change the direction of fluid. So that is the job of a fitting, either connect two pipes or change the direction. Basic types of pipe fittings: cast, forged, seamlessly drawn, or formed and welded. Fittings may be flanged, socket welded, butt welded, or threaded, as you can see here. A lot of fittings, as you can see, changing the direction of the flow, connecting the pipes. These are called fittings. Flanges. Flange connect pipes, valves, pumps, and other equipment to form a piping system. Flange face shall be protected and inspected for scratches and damages. So the flange face is the most important part of the valve. And there are different type of flanges, like neck ones, neck flanges, and raised flanges, like flat face, straight face, expansion joints. So you can see two types of expansion joints here. because every material has got a coefficient of thermal expansion. So normally for a long length pipes, you have a U-shaped expansion joints or something like this, which is rubber, so it can expand and contract without putting a lot of stress on the pipe joints or the pipe itself to compensate for that coefficient of thermal expansion. I mean, it's normal for every 100 feet you have, say, if you have a 300 degree Fahrenheit change in temperature, you have 2-3 inches of expansion, and that 2-3 inch need to be accommodated, and that is done by expansion joints, which is normally there are two types. This one is not very high pressure, so you can use a rubber one. This is for high pressure pipes, and it's more reliable, the U type. Piping supports holds pipe load, restricts vibration by clamping the pipe. A spacer may be used to avoid galvanic corrosion. So because normally the pipe is a different material than the pipe support. Supports are shoes, hangers, braces, and should be visually inspected for any problems such as accumulation of dirt, moisture, corrosion, galvanic corrosion. Pipe joining methods. Normally they are welded, threaded, or a flange is welded and then they are bolted together, two flanges. So flange, once the flange is welded to a pipe, it's called a spool. This chapter explains types of joints, provides several figures. Please study this. It's good for general knowledge and self-study. Chapter 6, reasons for inspection. The primary purpose of inspection is to achieve the desired quality assurance and ensure plant safety and reliability. This is not possible unless the damages, if any, are identified and quantified and repairs are carried out in order to restore the piping to the safe operating condition. Other reasons include personnel safety in case of a leak or failure resulting in unplanned shutdown and loss of revenue. So the reasons for inspection is primary reasons to identify and quantify the damages and then repair them to restore the pipe to the safe operating condition. And then obviously if you don't do that, it might end in failure and unplanned shutdown. It might have damages to the property and injuries to the human being, fatalities even, and then shutdown of the plant and obviously losing money or revenue. Normally, piping replacement schedule coincide with plant shutdowns. So the best time is to replace the pipes that you can no more repair it or it's too dangerous to use them is during the plant shutdown. But you keep monitoring it to make sure that it actually can work till the next inspection interval or the plant shutdowns or turnaround. Assessing the condition of piping allows sufficient time to procure or manufacture those piping that need replacement. Inspection is also required because of rules and regulations. For example, according to OSHA 1910, equipment and piping that carries significant amount of hazardous chemical shall be inspected as per accepted codes and standards such as API 570 for piping. Inspection plans. It should contain the inspection task, scope of inspection, and schedule. So there should be definitely a schedule required to monitor the identified damage mechanism, because inspection plan is time dependent. So it should tell you what activities you do, what inspection tasks you do, what is the scope of inspection, boundary limit, what schedule it is, how you do it, and for how to do it, it refers you to a procedure. API 570 defines the minimum contents of an inspection plan. Developing an inspection plan. First, gather information about inspection, operation, and maintenance history. Second, consult with piping engineer, corrosion specialist, and operators to find the type of expected damage and location. Third, select the NDE technique based on the expected damage, location, and limitation of the technique. Finally, address the CMLs, conditioning monitoring locations, which is the examination point, testing point, piping contact points, injection points, mixing points, soil to air interface, dead legs, corrosion under insulation, valve, expansion joint, positive material identification of material, vents and drains within the inspection plan. So you have to address all these areas. How you're going to check them, because these are CMLs, representative of the corrosion behavior of the metal over the years. Wall thinning to find the corrosion rate and the remaining thickness and the next inspection interval, and the vulnerable points such as piping contact points, injection points, mixing points, soil to air interface, dead legs, corrosion under insulation. They are important points, vulnerable, that you need to inspect, and you need to address them in the inspection plan. Shall be risk assessed periodically as per API 570. So you have to see that your inspection plan is effective. You are actually detecting what you expect from damage mechanism point of view, and the reliability of the plant is okay. And using 580 risk-based inspection techniques, prioritizing inspection of the equipment, critical equipment especially. Risk-based inspection plans are based on probability of failure and consequence of failure. In this method, inspection efforts are focused on those areas which has higher rate of failure, or when failure can cause grave consequences in terms of harming personnel or losing revenue and property. API 580 explains an RBI management system, while 581 describes the methodologies. 579 is about fitness for service evaluation that is used in conjunction with. To determine the likelihood of failure, we should know about the current condition of the pipe, the expected damage mechanism, and the effectiveness of previous inspection. For example, when a selected examination method used previously that was poor in detecting a particular defect, or when previous inspection reports show examination of areas with minimum damage or corrosion rate. In such instances, inspection and examination efforts should be diverted to the locations where there is a high possibility of developing defect, such as above mixing point at stress risers. So they might ask you high possibility of defect, which is a vulnerable area. It's above the mixing points and at stress risers. By knowing the type of damages expected, we could select appropriate examination method. For example, UT lamination check is best for detecting lamination, while RT method is poor to detect lamination, because lamination does not occupy much volume, so you would hardly see it on a radiograph due to nature of how radioactive waves work. There might be items or location where the likelihood of damage and defect is not high, but the consequences could be grave in terms of human life and plant shutdown. Such locations also deserve more scrutiny. On the other hand, when both probability and consequence of failure are low, inspection frequency and coverage could be reduced accordingly. RBI assessment should be fully documented, so when we review it periodically, we can understand what the basis of recommendation was and if the RBI input has changed over the time, warranting revisions of recommendation or making additional one. So the reassessment needs to be done from time to time in case, anyway, after every 10 years. And whenever there is a process change, there is a change in our initial assumption that we came to that conclusion. This is called management of change. RBI assessment shall produce the following: the most suitable NDE method, the extent or coverage and frequency of NDE examination and inspection, determining the inspection interval or the date for internal, external, and on-stream inspection, whether any pressure test required after repair and alteration to revalidate the piping performance or verify its integrity, any mitigating measures recommended, such as use of inhibitors, change of material for parts and piping. These recommendations are called non-inspection recommendations. Interval-based inspection plans to determine inspection interval, external, internal, visual, thickness measurement. Use API 570, which calculates the interval based on the corrosion rate and the remaining corrosion allowance. The frequency and time of inspection should be determined by the following conditions: severity of service, degree of risk, amount of corrosion allowance remaining, historical data available, regulatory requirements. On-stream inspection can reduce downtime by the following means: extending process runs and preventing unscheduled shutdowns, permitting fabrication of replacement piping before a shutdown, eliminating unnecessary work and reducing personnel requirements, aiding maintenance planning to reduce surges in workload. Piping system is marked up on the process flow diagram because it is the easiest way to group together the piping under same operating condition, and for better visibility they are color coded, identifying the boundaries. Piping circuit are subgroup of piping system. It's a group of pipe that not only under same or similar operating condition, pressure and temperature and fluid process like piping system, but also under same or similar environmental condition, material, and corrosion rate. So it's a subgroup of piping system, the piping circuit. Piping circuits are grouped to make field inspection and record keeping simple and easy. And piping circuit is marked on PNID. So process and instrumentation diagram, which is more detailed than process flow diagram or PFD. So piping system is marked on PFD process flow diagram, while piping circuit is marked on the piping and instrumentation diagram. And mostly you see PNIDs in the projects actually, because PFD doesn't give you much information. It's very crude, very general, too general to it just show you the overall picture. Statistical analysis of circuits, CML or conditioning monitoring location. This helps find the corrosion rate trends, thereby adjusting inspection intervals accordingly. Short-term corrosion rate are less reliable than long-term corrosion rate because of measurement accuracy and nature of corrosion, which is not uniform. Identifying locations susceptible to accelerated corrosion. Obviously, we are looking for the worst possible affected area. For example, when there is a change of shape, such as elbow, reducer, mixing point, or when there is a turbulence or impingement of fluid. Conditioning monitoring location shall be accessible, for example, areas near the ladder, on the platform, or at level height. This makes field inspection and examination easier and faster without the necessity to work at height or erecting a scaffold. It's just all common sense that CML should be accessible. Inspection for a specific damage mechanism. Always check upstream and downstream of damaged areas. The most susceptible points are corrosion under insulation, mixing point, injection points, dead legs, localized corrosion, erosion corrosion, contact point corrosion between the pipe and support, creep, brittle, and fatigue failure. Injection points and mixing points. See that the corrosion damage associated with inspection points may be 10 times more than the mainstream corrosion with localized losses, being the most common form of problem. So 10 times more. And injection when you do like inhibitor or so it's not the mainstream. Now the mixing points is when two mainstream meet. So mixing points can be subjected to accelerated damage either from corrosion or thermal fatigue because of difference in temperature and turbulence that is created when mixing two mainstreams. Table 4 shows the potential for thermal cracking at mix points if temperature difference between the two streams at mixing points exceeds certain limit. Thermal sleeve may therefore be needed to prevent thermal fatigue. Normally, over 200 degree Fahrenheit temperature swing is called, it can be treated as a thermal fatigue. Complete mixing may not happen until 100 pipe diameters or more downstream when at the mixing point. Dead legs may be removed if they serve no purpose because they keep the stagnant water, there is falling, and there is accelerated corrosion at dead legs. By dead legs, we mean that there is a pipe that is one end is blinded, or there is no flow or little flow. It also includes the branch pipe that is taken to connect it to pressure or temperature gauge. Corrosion under insulation. There is a range for which metal can, when corrosion under insulation can occur. Susceptible location or any sharp change of shape, such as connection or piping with valves and fittings, hangers, dead ends, bolting, and termination point of insulation. These are the susceptible areas for corrosion under insulation. Soil-air interface corrosion can be particularly aggressive between 12-inch deep underground to 6-inch above the soil due to abundant presence of oxygen, moisture, and soil. Internal corrosion is possible in the process service. These types of corrosion are usually localized and are specific to service. Example are downstream of injection and mixing point and upstream of product separators. It can be characterized corrosion by grooves, rounded holes, waves, and valleys in a directional pattern. So that is the morphology of erosion or erosion corrosion. Grooves, rounded holes, waves, valleys and it is a directional pattern. Combination of corrosion and erosion, called erosion corrosion, results in significantly greater metal loss than can be expected from corrosion or erosion alone. Erosion corrosion happens at high velocity and high turbulence areas. Environmental cracking. Examples include chloride stress corrosion cracking of stainless steel, austenitic, polythionic acid stress corrosion of synthesized steel, amine stress corrosion cracking, hydrogen blistering, and hydrogen-induced cracking. So, polythionic acid stress corrosion is sensitized steel, and chloride stress corrosion is for austenitic stainless steel. Corrosion beneath linings and deposits happens due to break or holes in the lining. Lining should be visually inspected for separation, breaks, holes, and blisters. Fatigue cracking happens due to cyclic loading, either mechanical, repeated increase or decrease in temperature, in pressure, and such as by also vibration, or thermal, repeated heating and cooling. or temperature swing. Creep cracking is plastic deformation of metal under constant stress below its elastic limit but under high temperature. So an example of where creep cracking has been experienced in the industry is 1 1/4 of chromium steel above 900 degrees Fahrenheit. This has been particularly highlighted. Carbon, low alloy, and other ferritic steel can fail by brittle fracture at or below ambient temperature, especially 2 1/4 chrome 1 mole material, which is widely used for pressure vessel. This material. So during a startup shutdown, and have to be careful that the ductile to brittle transition temperature doesn't happen for that particular material at that thickness, especially 2 1/4 chrome 1 mole material. Integrity operating windows includes temperature, pressure, fluid velocity, pH or acidity, flow rate, chemical or water injection rate, level of corrosive constituents, chemical composition, etc. Frequencies and extent of inspection depends on the risk of product or probability and consequence of failure. When piping must be replaced, on-stream inspection allows an inspector to define the extent of replacement necessary and have replacement piping fabricated before the turnaround. Signs of wet insulation should be noted when piping is offline. Safety precautions and preparatory work, decontamination and gas testing, isolation, communication, work permit, cordoning off, warning sign, proper PPE, they are the main areas where prevent any accident. Follow 2217, API 2217 guideline for safe work in inert confined spaces in petroleum and petrochemical industry. Remember, anything of API of 2000 series is about the safety. Hammer testing of pressurized piping might cause failure, so don't hammer test when pipes is pressurized or under pressure or working. Some terms, important terms is explained here. Leaks can be safety or fire hazard, always result in economic loss. Temporary or permanent repair can be made while the lines are in service. Misalignment. Piping should be inspected for misalignment. Pipe dislodged from support, vessel ball deformation, pipe supports out of plumbness, excessive replacement of bearing, shifting of base plates, foundation damage, cracks in connecting flanges, expansion joints not performing properly are all indication of misalignment. Supports are shoes, hangers and braces and should be visually inspected for any problem, like accumulation dirt and galvanic corrosion. Vibration, vibrating or swaying piping should be inspected for cracks at the point of restraint, usually in the areas of anchors or where a small bore pipe is attached to the main line. Coating, defects in the protective coating and installation will permit the moisture to come into contact with piping. This can result in corrosion and metal loss. So any coating damage. Accumulation of corrosive liquids. Some liquids are corrosive to steel piping. Spills should be cleaned up or neutralized. Hot spots. Operating the piping at higher than design limits may cause bulging even to the point of failure. Investigation of these areas is essential. Borescope is used to inspect the piping internally. And cracks is the most dangerous types of defect. Inspect the susceptible locations, construction tack wells at other than pressure wells, heat affected area, joining wells and joints of restraint or excessive strain. include locations that are subject to stress corrosion cracking, hydrogen cracking, and caustic or amine embrittlement, as well as exposed threads. Check gasket faces of flanges. Pressure test. Pressure tests are strength tests that may be used on the following: underground lines, water and other non-hazardous utility lines, long oil transfer lines in areas where a leak of spoil would not be hazardous to the personnel or harmful to the environment. Complicated manifold systems, small piping and tubing system, all systems after a chemical cleaning operation. Various fluids may be used for pressure testing: water, with or without an inhibitor; liquids, products normally carried in the system if non-toxic and non-flammable; steam, air, carbon dioxide, nitrogen, helium, or other inert gas; pneumatic or gas test, which is another version of pressure test and used when hydro test with liquid medium is not possible. Using salt water as a test medium can create problems like pitting and corrosion. Pneumatic tests should be conducted strictly in accordance with ASME B31.3. Do not hammer test on cast iron, stress relief lines in caustic and corrosion service and piping under pressure. Soil resistivity testing, the Venner method, the soil bar and soil box methods are discussed. Basically, each method measures a voltage drop or IR drop caused by a known current flow across a measured volume of soil. The resistance factor is used in a formula to determine the resistivity of the soil. Leak testing, the basic method of leak testing, underground piping or pressure decay method. So you put it under pressure and see if there is any pressure drop. So that means it's leaking somewhere because you can't see the underground piping. Volume in, volume out method, how much you have injected, how much came out. So that can, if that can be measured. Single point volumetric method, marker chemical tracer method, so I can detect any leak by that tracer gas. Acoustic emission method, where if the pipe is under pressure and actually a crack is developing, so there is some probes that actually amplify the sound, uh, and that's hence acoustic emission. And detect this crack growth. Determination of retired thickness, API 570 permits use of Barlow formula to determine the required wall thickness for in-service piping, which is for D less than 6 or PSC less than 0.385. Most of the pipes are there, right? The wall thickness is less than 1/6 of the diameter. Most of the pipes are wall thickness less than 1/6 of the diameter. So this formula applies, otherwise some other formula you have to use. Slightly different. So wall thickness, the required design thickness means pressure into diameter divided by twice of allowable stress. And if longitudinal joint efficiency is required, then you have to add it. If it is 1, then you don't use it. Obviously, it's 1. It doesn't change the result. Table 7 shows minimum thickness for carbon and low alloy steel on page 105. Um, Chapter 13 shows list of records and provides a sample template, and Annex A shows sample external inspection checklist for process piping. Thank you.